So, today I'm going to talk about nuclear fusion. So far we've reached about 10 seconds after the Big Bang. The constituents of the universe were protons, which comprised about 50% of the mass of the universe that we could see. I'm not including the dark matter here. Neutrons, which consisted of the other 50%. Electrons, and radiation. So, after about 10 seconds, a process called nuclear fusion began. Taking 2 protons and 2 neutrons, the process of fusion involves them sticking together. And the result is called an alpha particle, or sometimes it's called the nucleus of the helium atom, because as we'll see later, these particles became the centre of atoms. And this process of fusion ends after about 20 minutes, when the universe is so big and so cool that there's not enough energy to fuse these particles together. Now, the picture that I've given here is oversimplified. You don't just have 2 protons and 2 neutrons sticking together. There is a series of steps. But in any case, the universe needed to be fairly hot for this to happen. And as the universe expanded, it cooled. 20 minutes afterwards, it wasn't hot enough for this to happen. So the process of fusion is actually quite complex. You don't just take 2 protons and 2 neutrons and stick them together. There are a series of steps whereby it happens. Fusion still happens in stars today, although the process is different from that which happened in the Big Bang. And I'll talk about how stars perform fusion and the result of that later on in the story. In any case, the result of fusion is the release of energy. What happens is that if you take particles, 2 protons and 2 neutrons, when they are separate, they weigh more than after they are stuck together into this alpha particle. So we lose mass, but you cannot lose energy, so the energy of mass is converted into radiation eventually, and this is the radiation that we receive from stars. So, as I say, it's the same process in stars, or the same result in stars today, although the process is slightly different. So, as time went on, the universe expanded, radiation inside was stretched out, and the particles travelled slower. And I've tried to show that with this little diagram of them starting off very quick and moving slower. As they move slower, so they have less energy, less heat, and the universe cooled. So there was not enough energy, they were not travelling fast enough to fuse together, so fusion stopped after about 20 minutes. There were still some neutrons which had not found their way into alpha particles. These were free neutrons. And it turns out that free neutrons are unstable. They decay because of the weak nuclear force. So the neutron breaks down into an electron, a proton, and another particle which I have not discussed so far, called an antineutrino. So after about 15 minutes, half the free neutrons had decayed through this process, and 15 minutes later another half of the free neutrons decayed. So this is called the half-life, the time it takes for half of particles to decay by this radioactive process. And the half-life of neutrons is about 15 minutes. So by the time we reach today, 13.8 billion years later, there are almost no free neutrons left in the universe, although there are probably one or two. So after all this process had happened, fusion and the decay of neutrons, the result was that the universe consisted of protons, about 75% of the mass of the particles that we could see, the alpha particles, which consisted of about a quarter of the mass of the particles that we could see, and then the very light electrons and the radiation. So thank you for watching, and if you want more information about the history of the universe, visit my website historyoftheuniverse.com.